Hi guys, so tonight we're going to talk about discontinuities. Just a reminder that if a graph is continuous, it means you can trace it without lifting up your pencil. So both of these graphs are discontinuous. The first graph is discontinuous because there's a hole in the graph. So you can see that the graph you're going, and then there's a hole in the graph right here. So you have two pieces that connect with an open circle. The other type of discontinuity is this second graph where we have what's called a jump. And that's where we have two pieces that don't connect at all. Both of these functions are discontinuous. So what we're going to do right now is we're going to explore limits a little bit. And I want to look at when x is -3 because that's where we get a hole in the graph is at -3. So I'm just going to draw, here's -3. And what we're going to do is we are going to approach -3. And so if I have just this imaginary asymptote here at -3, um, let's say that we are coming into -3 from the left-hand side. So how we would write that is we would write the limit as x approaches -3 from the left-hand side. Graphically, you can see that I'm getting closer as x is getting closer and closer to -3. Y is getting closer and closer and closer to 2. Now, it doesn't matter that when I'm actually at 2, I equal -2. So if I said, what is P of -3 on this graph? Well, you would say P of -3 equals -2, which is this point here. But limit just means what am I approaching? So as I'm getting closer and closer and closer to -3 from the left-hand side, here I am coming in, I am getting closer and closer and closer to the y value of +2. So that is the limit. Now you can do the limit algebraically. So you can see here's the equation of the piecewise graph. If I'm coming in from the left-hand side, it means I would be using this piece right here. So we would take 1/3, and in place of x, I'm going to go ahead and put in -3. And then I'm going to add 3. And you can see that those are going to cross cancel, giving me -1 plus 3, which equals 2. And you can see that was my limit right here at 2. Now let's talk about the limit as I approach x equals -3 from the right-hand side. So looking at, let me grab a highlighter. So this is coming in to -3 from the left-hand side. Now I'm going to come into -3 from the right-hand side over here. So here I am, I'm coming into -3, and you can see this graph as I'm coming closer and closer and closer to x equals -3, y is getting closer and closer and closer to 2 again. So let's go ahead and write that as a limit notation. This would be the limit. Oops, I need a marker. The limit as x approaches -3, and then you put a plus, meaning from the right-hand side, f of x is going to equal +2 again. Again, if I'm actually at -3, I equal -2. But a limit is just what am I approaching? I'm approaching 2. So let's plug it into the function algebraically and see what happens. So the part that's on the right-hand side is going to be this second piece of the graph. So you would have the absolute value, and then again, we're going to put in -3, subtract 1, absolute value, subtract 2. This is the absolute value of -4, subtract 2, which is 4 subtract 2, which equals 2. So you can see my limit for both is 2. Now, because p of negative 3 does not equal 2, we know that there has to be a point of discontinuity. So there is a point of, let me scroll a little bit, a point of discontinuity at x equals negative 3. All right, let's look at the next problem. So looking at this next problem, we have what's called a jump. So looking at the jump, we're going to do the same thing. We are going to come into negative 3 again, because that's where the graph is breaking. So let's see what happens to the limits as I come in to negative 3. So from the left-hand side, you would say the limit as x approaches negative 3. F of x is equal to, and you can see we're coming in from this side, and it looks like it's equal to negative 2. All right. Now let's look at the second part. So the second part is going to be the limit as x approaches negative 3 from the right-hand side. And I forgot the minus here. Left-hand side, and now we're doing right-hand side. From the right-hand side, f of x equals. Well, let's look at this again. And here we go. We're coming in from this side. Here we go. Here's x. We're coming in from this side. And y, as we come in, is getting closer and closer and closer and closer to negative 4. Now, it doesn't matter that negative 4 is undefined. It just matters, what am I approaching? All right. And so I'm getting closer and closer and closer and closer to negative 4. Let me show you how this works algebraically. So we're going to plug negative 3 in, and if we're coming from the left-hand side, so here I am, and I'm coming in the bright pink from the left-hand side, the limit is negative 2. So what does that look like algebraically? You come up to the piecewise function, you pick the piece that's on the left-hand side, and that's this parabola piece, all right? And you would have the opposite of negative 3 plus 6 squared plus 7. The opposite of 3 squared plus 7. 3 squared is 9, so the opposite of 9 plus 7 equals negative 2. And sure enough, right here, the limit from the left-hand side was negative 2. All right, let's look at the limit from the right-hand side. So if you look at the purple, the limit from the right-hand side as I come in is going to be negative 4. Let's do that algebraically. So I'm going to use the piece that's on the right-hand side. That's the piece that I'm following. So it's the opposite of the square root of negative 3 plus 3 subtract 4. The opposite of 0 subtract 4 is negative 4. And sure enough, that was my limit, was negative 4 from the right-hand side. So if we look at these two limits, we can see that both pieces approach different y values. One piece approaches a y value at negative 2, and the other piece approaches a y value at negative 4. Because of that, we know that at x equals negative 3, there is a jump discontinuity in the graph. So let's write that down. Since both pieces approach different y values, we have a jump, discontinuity at x equals -3 because both pieces approach different, I'm just going to put DIFF, y values. Looking at the discontinuities in the graphs of piecewise functions, let's look at number 1. And what we want to do is write an equation. So I think I'm going to start with the absolute value equation. That one looks like it might be a little bit easier. So we would write f of x equals, and this is going to be a piecewise function. This is the absolute value of x. It got shifted to the left 1 and up 2. So it'd be the absolute value of x plus 1 is going to take me left 1, and then plus 2 is going to take me left 2. And that piece only, the domain of that piece is -4 to 4. So in red, I'll put the domain x is greater than -4, but less than +4. All right, the second piece, it looks like there's all sorts of reflections on that second piece. So it's a square root graph. So you can see here's what a square root graph looks like originally. This square root graph appears to have been reflected in the other direction. So this is going to go in this direction, you can see. And then you can see that this piecewise graph got moved to the left 4 and up 5. So if you had the square root and you went x plus 4, that's going to move you left 4, and then plus 5 is going to move you up 5. However, we have a reflection over the y-axis. So the reflection over the y is going to put the negative in here as x plus 4 and then plus 5. Now the stretch looks pretty much the same as normal. It's right 1, up 1, so I don't have to worry about stretches. This one, same thing. It was right 1, up 1, so there's no stretch. This is going to simplify as the square root, and you're going to distribute that negative. So negative x, that's the reflect over the y, subtract 4. Subtract 4 is really plus 4 when you factor that negative out. And then you have plus 5. Now this graph, it looks like it's going to be open at -4, but closed at -8. So x is between -8, and this would be equal to, because of that closed point, and -4. So there are the equations for that piecewise graph. Now, based on the graph, let's answer the questions. As x approaches -4 from the left, so as I'm coming into this function from the left-hand side, as x is getting closer and closer and closer to -4, I'm approaching this open circle here. So the limit is going to be where that open circle is, which is 5. As x approaches -4 from the right, so as I'm coming into -4 from the right, I'm getting closer and closer and closer and closer to that open circle, which is also at 5. Because those numbers are the same, I know that I have a discontinuity at a point instead of a jump. If these two numbers are different, then I have a jump. Otherwise, it's a discontinuity at that point. So number 3, let's write the limit. It would be the limit as x approaches -4, little minus from the left, f of x equals 5. The second part, the limit as x approaches -4 from the right, f of x equals 5. Since those points are the same, and because f of -4 is not defined, we know that there's a hole in the graph. So let's quickly look to see how we get 5 algebraically for both pieces. Algebraically, if I take the left piece and I plug in a -4, so I have the opposite of -4 subtract 4 plus 5. Those are going to become a negative, and a negative is a positive, and 4 minus 4 is 0. The square root of 0 plus 5 is equal to 5. So that's the first piece that I found just by looking at the graph. This is looking at it algebraically. How did I get the second piece to equal 5? Well, this piece is on the right-hand side. So let's plug it into the right-hand side of the graph. Absolute value of x plus 1 plus 2. In place of x is going to be -4. So -4 plus 1, the absolute value of -3 plus 2. 3 plus 2 equals 5. Check, that equals 5. And so we know because these both were the same, there is a hole or a point of discontinuity at x equals -4. All right, the rest of these we'll end up doing in class and in groups together.